And I'm now going to show you the benefit of everything that I've just said. And remember the factory diagram. On the x-axis is tokens per second throughput, in the y-axis, tokens per second throughput of the factory, and the x-axis, tokens per second of the user experience. And you want super smart AIs, and you want to produce a whole bunch of it. This is Hopper. Okay, so this is Hopper, and it can produce for one user, for each user, about 100 tokens per second. This is 8 GPUs, and it's connected with InfiniBand, and I'm normalizing it to tokens per second per megawatt. So it's a 1 megawatt data center, which is not a very large AI factory, but anyhow, 1 megawatt, okay? And so it can produce for each user 100 tokens per second, and it can produce at this level, whatever that happens to be, 100,000 tokens per second for that 1 megawatt data center. Or it can produce about 2.5 million tokens per second, 2.5 million tokens per second for that AI factory if it was super batched up and the customer is willing to wait a very long time. Okay, does that make sense? All right, so nod. All right, because this is where, every GTC, there's the price for entry, you guys know, and it's like you get tortured with math, okay? This is the only at Nvidia do you get tortured with math. All right, so Hopper, you get 2.5. Now, what's that 2.5 million? How do you translate that? 2.5 million. Remember, ChatGPT is like $10 per million tokens, right? $10 per million tokens. Let's pretend for a second that's. I think the $10 per million tokens is probably down here. Okay, I'd probably say it's down here, but let me pretend it's up there. Because 2.5 million, 10, so $25 million per second. Does that make sense? That's how you think through it. Or on the other hand, if it's way down here, then the question is, so it's 100,000, just divide that by 10, okay? $250,000 per factory per second. And then, it's 31 million, 30 million seconds in a year. And that translates into revenues for that 1 megawatt data center. And so that's your goal. On the one hand, you would like your token rate to be as fast as possible so that you can make really smart AIs. And if you have smart AIs, people pay you more money for it. On the other hand, the smarter the AI, the less you can make in volume. Very sensible trade-off. And this is the curve we're trying to bend. Now, what I'm just showing you right now is the fastest computer in the world, Hopper. It's the computer that revolutionized everything. And so how do we make that better? So the first thing that we do is we come up with Blackwell with NVLink 8. Same Blackwell, that one same compute, and that one compute node with NVLink 8 using FP8. And so Blackwell is just faster. Faster, bigger, more transistors, more everything. But we like to do more than that, and so we introduce a new precision. It's not quite as simple as 4-bit floating point, but using 4-bit floating point, we can quantize the model, use less energy to do the same. And as a result, when you use less energy to do the same, you could do more. Because remember, one big idea is that every single data center in the future will be power limited. Your revenues are power limited. You could figure out what your revenues are going to be based on the power you have to work with. This is no different than, like many other industries. And so we are now a power limited industry. Our revenues will associate with that. Well, based on that, you want to make sure you have the most energy efficient compute architecture you can possibly get. Then we scale up with NVLink 72. Does that make sense? Look at the difference between that NVLink 72 FP4, and then because our architecture is so tightly integrated, and now we add Dynamo to it, Dynamo can extend that even further. Are you following me? So Dynamo also helps Hopper, but Dynamo helps Blackwell incredibly. Now, yep. Only at GTC do you get an applause for that. And so now notice what I put, those two shiny parts, that's kind of where your max Q is. You know, that's likely where you'll run your factory operations. You're trying to find that balance between maximum throughput and maximum quality of AI. Smartest AI, the most of it. Those two, that XY intercept is really what you're optimizing for. And that's what it looks like if you look underneath those two squares. Blackwell is way, way better than Hopper. And remember, this is not ISO chips. This is ISO power. This is ultimate Moore's Law. This is what Moore's Law was always about in the past. And now here we are, 25x in one generation as ISO power. This is not ISO chips, it's not ISO transistors, it's not ISO anything. ISO power, the ultimate limiter. There's only so much energy we can get into a data center. And so within ISO power, Blackwell is 25 times. Now here's that rainbow, that's incredible. That's the fun part. Look, all the different underneath the Pareto, the frontier Pareto, we call it the frontier Pareto, under the frontier Pareto are millions of points we could have configured the data center to do. We could have parallelized and split the work and sharded the work in a whole lot of different ways. And we found the most optimal answer, which is the Pareto, the frontier Pareto, okay, the Pareto frontier. And each one of them, because of the color, shows you it's a different configuration. Which is the reason why this image says very, very clearly you want a programmable architecture that is as homogeneously fungible as possible, because the workload changes so dramatically across the entire frontier. And look, we got on the top, expert parallel 8, batch of 3000, disaggregation off, Dynamo off. In the middle, expert parallel 64 with the 26% is used for context, so Dynamo is turned on, 26% context, the other 74% is not. Batch of 64, and expert parallel of 64 on one, expert parallel 4 on the other. And then down here, all the way to the bottom, you got tensor parallel 16 with expert parallel 4, batch of 2, 1% context. The configuration of the computer is changing across that entire spectrum. And then this is what happens. So this is with input sequence length. This is a kind of a commodity test case. This is a test case that you can benchmark relatively easily. The input is 1,000 tokens. The output is 2,000. Notice earlier, we just showed you a demo where the output is very simply 9,000, right? 8,000, okay? And so obviously this is not representative of just that one chat. Now this one is more representative, and this is what, the goal is to build these next generation computers for next generation workloads. And so here's an example of a reasoning model. And in a reasoning model, Blackwell is 40 times the performance of Hopper. Straight up. Pretty amazing. I've said before, somebody actually asked, why would I say that? But I said before that when Blackwell starts shipping in volume, you couldn't give Hoppers away. And this is what I mean. And this makes sense. If you're still looking to buy a Hopper, don't be afraid. It's okay. But I'm the chief revenue destroyer. My sales guys are going, oh no, don't say that. There are circumstances where Hopper is fine. That's the best thing I could say about Hopper. There are circumstances where you're fine. Not many. If I had to take a swing, And so that's kind of my point. When the technology is moving this fast, and because the workload is so intense, and you're building these things, they're factories. We really like you to invest in the right versions. Okay, just to put it in perspective, this is what a 100 megawatt factory looks like. This is a 100 megawatt factory. You have, based on hoppers, you have 45,000 dies, 1,400 racks, and it produces 300 million tokens per second. Okay, and then this is what it looks like with Blackwell. You have 86. Yeah, I know. That doesn't make any sense. Okay, so we're not trying to sell you less. Okay, our sales guys are going, Jensen, you're selling them less. This is better. Okay, and so anyways, the more you buy, the more you save. It's even better than that. Now the more you buy, the more you make, you know? And so anyhow, remember, everything is in the context, everything is now in the context of AI factories. And although we talk about the chips, you always start from scale up. We talk about the chips, but you always start from scale up, the full scale up. What can you scale up to the maximum? I want to show you now what an AI factory looks like, but AI factories are so complicated. I just gave you an example of one rack. It has 600,000 parts. You know, it's 3,000 pounds. Now, you've got to take that and connect it with a whole bunch of others. And so we are starting to build what we call the digital twin of every data center. Before you build a data center, you have to build a digital twin. Let's take a look at this. This is just incredibly beautiful.